So thank you very much for inviting me to this colloquium. So first of all, I would like to give you an overview of what I'm doing in the field of organic spintronics. So it includes three interdisciplinary parts. So giant magnetoresistance in organic spin valves, in which I study the sandwich device, the organic layers sandwiched between two ferromagnetic electrodes. And I study the spin injection, spin detection, spin transport, and the spin manipulation inside the device. The second topic that I am working on is the magnetic field effects in organic light-emitting diodes. You can see the device here is almost identical to the organic spin valves device, but here we use a non-magnetic electrode. So the effects was discovered by our group at the University of Iowa in 2004. And you can see here, when you put the device into the magnetic environment, you can change the conductivity of the device up to 30% and the electroluminescence up to 60%. This is a surprising result, and when we reported it, no one believes us. But now it is very well known that the effect exists. So here I work, in this topic I work for about 8 years already. And the third topic of my research is about the magnetic resonance, in which I use the optical detected magnetic resonance, conductivity detected magnetic resonance to study spin-spin interaction in organic materials. So because the time is very limited, so I would like to present only the first part of my presentation. If you have any questions about those two, we can discuss after the colloquium. I would love to do that. Okay, so here is the collaborator. At the University of Utah and other institutions, I would like to say thanks to for the financial support from DOE and NSF. So this is the outline of my presentation. So first of all, I would like to give the introduction to organic semiconductor and organic spintronics. And then I will present the first organic spin valves reported by the Utah group in 2004. And then I move to the parts that I can prove that the spin of electron is actually transported in the organic semiconductor by two experiments that we have done at the University of Utah. And I give you some method that we can actually manipulate the spin of the electrons, and finally some application. So first of all, about the organic semiconductor. So it can be classified into two groups here. One is small molecule and polymer, depends on their sizes. So you can, the size of the small molecule is small, but for polymer you have n repeat units like this, and here can be up to 1,000. So the interesting points in those materials is that in the carbon-carbon bonds here, you have the single bonds and double bonds. The single bonds is the sigma bonds. This is a very strong bonds of about 10 electron volts. So it is impossible to break this bond. But the double bond here includes one sigma bond and one pi bond. And the electron in the pi bonds can be relocalized in order to form the electronic properties of those materials. You can see all of those materials have the double bonds, which means they have pi electrons. And the interesting point in the organic material is that you can engineer the spin-spin interaction like a hyperfine interaction or spin-orbit coupling. So you can see in those materials, iridium PPY here has the iridium heavy metal inside the small molecule. So the intrinsic organic semiconductor is very large because the intrinsic spin-orbit coupling goes like the number of protons to the fourth. So here we have the very large spin-orbit coupling. Here we have very small one because the number of protons in carbon is 6, is small. Or you can engineering even the hyperfine interaction here. If you replace the hydrogen by the deuterium, actually you change the hyperfine interaction inside the organic materials. So let me talk a little bit about the transport in the organic materials. Let's consider a single chain, polyacetylene chain. As you can see here, we have many pi electrons. So those pi electrons form bands in the single chains like this. The lower bands is fully occupied and the upper one is empty. So in the language of molecular orbital theory, the red line here is the highest occupied molecular orbital, and the lowest one here, the blue line here is lowest unoccupied molecular orbital. And the gap between LUMO and HOMO is about 1.5 to 3 electron volts, depending on the length of the polymer that we have here. So this is very good materials for light-emitting diodes, because here the gap in the visible range, and also for the organic solid cells. So if you put one electron into the chains here, the electron will move around under the, for example, the electric force with the high mobility, because this is the band-like transport. But inside the organic device, if electron, we have many chains, and if electron want to move from one chain to the other chains, it needs to hop from one to the other. And the hopping transport normally has a very low mobility, and the mobility is strongly dependent on the electric field, the temperature, and also the defects in the materials. Okay, so now if I want to make the device like organic light emitting diodes, I want to inject one electron into the unoccupied bands and one hole in the occupied band. At the time I have to use 2 electrodes. So the electrode that I use for injecting the electrons need to have the Fermi energy close to the LUMO band, and for the holes close to the HOMO band. If not, I have to apply a big voltage in order to inject the electron and holes. And why organic devices? So the big advantages of the organic devices is the low cost processing. We can make the organic film by many methods: drop cast, spin cast, thermal evaporate, or even we can put the organic solution inside the inkjet printer in order to print a very nice film on the plastic substrate, for example. And here is some application about the TV screens using OLEDs as pixels. The organic solar cell produced by Konaka. This is the company from Professor Alan Heger. And even you can use organic material for the organic field effect transistor. Okay, so now I would like to go to the spintronics part. So you know that the electrons has spin and charge, and the spin can be up or down, depends on the motion around itself. So the spintronics try to exploit the intrinsic spin of the electrons instead of the charges. So the reason is the current electronics device is approaching the limit. Some limitation in size. You can make the device smaller than 10 nanometer, and also in the speed. So the device cannot be faster than a few gigahertz. And also it consumes too much energy. So people try to look for the other kinds of device in order to overcome those limitations. So a Spintronics device is the one that a lot of scientists are doing. So let me tell you about a few spin-dependent organic semiconductor devices. So the OLEDs here is actually the spin-dependent organic semiconductor device, in which we use two non-magnetic electrodes, either calcium for the electron injection and gold for the hole injection, with the arbitrary direction of the spin. Remember, we don't control the spin direction here. And when electron and hole see each other, they can form the electron-hole pairs under the Coulomb force. And the pair can be triplets or can be singlet. And only singlet can emit light. So this limits the EL quantum efficiency of the device at 25%. So this is actually the spin-dependent organic semiconductor device, because the emission is come from the singlet. So somehow you can control the singlet population, which means you can enhance the emission of the device. I mean the electroluminescence quantum efficiency of the device. Okay, so the second device is organic spin veils, in which we use two ferromagnetic electrodes. And this is the unipolar device, because we only inject hole into the material and detect holes the other electrodes. Okay, so here is the scheme of the device. We have two ferromagnetic electrodes, one which injects the spin-aligned electrons at one electrode, and the other electrodes we use to detect the spin-aligned electrons from the first electrodes. And it turns out that the resistance of the device is strongly dependent on the magnetization of the two electrodes. So normally in this configuration you have small resistance, and this configuration we have the larger resistance. So, but how to inject the electrons with the spin aligned into the semiconductor effectively? So there's a huge problem here. Why? Because the ferromagnetic material normally has a low resistance, and the semiconductor has a large resistance. So it's caused the problem, namely the resistance mismatch between the electrodes and the semiconductor. And this problem was figured out by those theorists. Okay, so let me give you the very simple calculation so to see how those resistance mismatch come to the device. Okay, let's consider the two spin channel current model, in which I consider spin up and spin down are in two independent channels. So this is for the spin up, and this is for the spin down. And for this configuration, and this is the scheme for the anti-parallel configuration. And so now it is very easy to calculate the resistance in each cases. And the magneto resistance is just the resistance difference between the anti-parallel configuration and the parallel configuration. So if you do a little bit math, and then you can end up with this formula, in which B is this ratio, and alpha here is the ratio between the resistance of the semiconductor and the magnetic electrode. And so let's do the simple math. Alpha here is normally 1,000. You put 1,000 here, the denominator is so big. And then at the time, the magneto resistance here is less than 0.1%. This is the serious problem. For something less than 0.1%, you cannot do anything. So it turns out that we can control the resistance mismatch problem by some strategy. For example, alpha here, we can use, actually we can do some tricks in order to reduce the value of alpha by using the ferromagnetic semiconductor. So one semiconductor, the other semiconductor, they have similar resistance. So alpha here is small. So this is one way people do. The other way here is using the 100% spin polarization. 100% spin polarization means you don't have the spin down current, which means P here is equal to 1, and eventually you can cancel the dependence of the alpha, of the magneto resistance on alpha. So this is the way that we use in our lab. The other way that people use is using the thermal barrier or spin filter to decouple between the semiconductor and the magnetic electrode. Okay, so let me give you 3 ways that people involve community, organic community, in inorganic community use to inject the spin alike carrier into the organic material, into the semiconductor materials and detect it. The first scheme is they use the circularly polarized light in order to create the carrier with the spin in certain direction, and then detects the circularly polarized photoluminescence at the other place. So this is one way that people has done. The other way is, like I told you, use one ferromagnetic electrode for spin injector, and the other one is for the spin detector. And the third scheme here is actually between 2 of these. They use one ferromagnetic electrode to inject the spin alike carrier into the semiconductor, and then detect the circularly polarized electroluminescence inside the device. And actually this is the method that people use at first to prove that actually they can inject the spin alike carrier into the semiconductor. And it was done by two groups in this Nature paper at the same time in 1999. Okay, the way that the device that they had is they used a ferromagnetic semiconductor injector here, gallium manganese arsenide, for the hole injector, for the spin alike holes. Injecting into the gallium arsenide spacer, and then they detect the circularly polarized electroluminescence from the device, from the gallium arsenide spacer. But unfortunately, we cannot do it in organic semiconductor. Why? Because the photoluminescence or electroluminescence in the organic semiconductor is from the excitones with the very weak LS coupling, so we cannot use this method in organic semiconductor. Okay, so here is the schematics of the spin valves in general. They have a base spacer sandwiched between 2 ferromagnetic with different cohesive field. One is large and one is small, and the spacer here can be copper, can be insulator like aluminum oxide, can be inorganic or organic semiconductor, small molecules, something like that. And the ferromagnetic electrodes can be iron, cobalt, nickel, and those materials had different spin polarization, different capability to inject the spin alike carrier into the organic semiconductor or to the spacer. Okay, so let's study what is the spin polarization here. So the spin polarization is defined by the number of the carrier with the spin up minus the number of carrier with the spin down at the Fermi energy. This is very important, at the Fermi energy. And you can see the nickel ferromagnetic material here. The number of the spin out at the Fermi energy is slightly larger than the number of the spin up at the Fermi energy. So you can see the polarization here is minus 23%. This is small spin polarization materials. But if you consider the LSMO, the Fermi energy lies just in one spin electron band. So which means the spin polarization here is 100%. And in this table, I give you some idea about the spin polarization of iron and other materials, and also the Curie temperature and the work function. You can see the work function here is quite high. Those materials are good for only the hole injectors, not for the electron injectors.
Sorry, what is the number of electrons on the Fermi surface?
Oh, I don't know. The number of electrons on the surface,
So n
here?
up here or down here. So this is, you said this is the number of electrons on the Fermi surface?
Yes. At the Fermi energy, yeah.
So does it have the dimension of 1?
Yeah, 1 because we don't have the spin down. So 1 means 100%. Yes.
No, I mean, this is dimensionless quantity, or is it, or does it have dimension?
Or the n.
Oh, and here the number.
So it's the density of states, not the number.
Density of states.
Yeah, the density of state. Yeah, thank you for verifying it. Yeah. Okay, so now I would like to give you an example that I can change the magnetization of the electrodes using the external magnetic field. And you can see here, this is the cobalt and LSMO. This is two ferromagnetic electrodes. LSMO has a coherence field of about 5 millitesla, and cobalt has a coherence field of about 15 millitesla. And when I use the external magnetic field, you can see the magnetization change from parallel to anti-parallel and parallel again. So when the magnetization of the electrodes change its direction relative to each other, we also the resistance of the device changes. So you can see for the parallel magnetization, the resistance is low. And anti-parallel, the resistance is high. Okay, so I would like to give you two examples of spin wave structure. So in the first example, the spacer is copper. Okay, so in one electrode, I used to inject the spin down electrons to the copper. And this spin allied carrier moved to the other electrode under the effect of the electric field. And then at the second electrode, there's two possibilities here. The first possibility is that we have the state. We have the large density of states for the spin down. So the second electrode can accept this spin. So which means the resistance of the device is low. But in the other case, if we don't have any density of states for the spin up at the second electrode, what happens in this situation? The spin here has to reflect back. This brings to the high resistance of the device. Okay, so this is the magnetic response of this giant magnetoresistance. Copper and nickel ion as the spin injector and detector. And this is the giant magnetoresistance. Why is it giant magnetoresistance? Because it's so large. This is 10% and more than 10%. But it's not like that. I would like you to know more than that. So giant magnetoresistance is relative to spin injection from one ferromagnetic electrode to the spacer, and then it's relative to spin transport. This is very important concept of the giant magnetoresistance. Okay, the other example is you will see, this is tunneling magnetoresistance, in which we use the aluminum oxide as a spacer. And you can see in this configuration, there is no concept of the spin transport here. But you can see the magnetic response are identical because the principle for accepting or rejecting the injected spin, electron spin are the same in the giant magnetoresistance. So in this case, we call the tunneling magnetoresistance. This is not giant magnetoresistance. So the spin aligned carrier just tunnel through the insulator without any spin transport. Okay, so what is the advantages of the organic spintronics? So everyone knows this sentence very well because it has been repeated many times. So the spin relaxation time in the organic material is very long because the weak hyperfine interaction and also weak spin orbit coupling in the materials. The second advantage is that when you deposit the organic film on top of the ferromagnetic materials, you form the tunneling barrier, insulator barrier at the interface already naturally. So this interface can help you to overcome the resistance mismatch problem that we talked in the previous slide. So also we can dope the materials in order to enhance the conductivity. We can have the light emission activity from the device, like OLEDs and spin OLED. I will introduce this later to you. And finally, we can have the device with all organic by using the organic ferromagnet semiconductor. Okay, and we are working on this possibility. Okay, this is the vertical spin wells in our group. So we have the LS symbol to inject 100% spin polarization into the organic layer. The organic layer here can be small molecule or polymer, and we use cobalt, nickel, or iron as a top electrode. Okay, so now we understand a lot about about spintronics in general already. So I would like to move to the first device, organic device, had been done was reported by the Utah group. Okay, this is the device that they use AOQ3 as a spacer, and LSMO and cobalt as electrodes. And so you can see here the SEM, in the SEM image, we have the well-defined layers, and it tells us that this is the good device. And here is the band diagram of the device. You can see LSMO, Fermi energy, and Fermi energy of the cobalt are close to the HOMO level. So this is a very good materials for hole injector and detector. So the IV characteristics show you that this is really a unipolar device. Okay, so the magnetoresistance in the previous device was reported in 2004 in the Nature from Vadeni group of about 40% at low temperature. So, and at this time they claim giant magnetoresistance. So you can see, which means they claim that the effect is relative to spin injection and spin transport inside the organic materials. Okay, so here is some result of the thickness dependence. They make device AOQ3 organic spin well device with different thicknesses, and you can see the thicker is the device, the smaller is the magnetoresistance. The magnetoresistance here is just less than 2%. And they plot all of the thickness dependence of the magnetoresistance in one plot here, and fit those experimental data with the well-known modified Julia model in which P1, P2 here is the spin polarization of the electrodes. D here is the thickness of the device, and lambda S here is the spin diffusion length. And D naught here is something they call the ill-defined layer. Okay, let me tell you about what happens for the ALQ3. ALQ3 is a very soft materials. When you thermal evaporate the cobalt electrodes on top of the ALQ3, the hot cobalt particle penetrates into the ALQ3 at a certain depth. Okay, and the depth there is D naught. They don't know what it is, but how thick it is. But it turns out that we can get this kind of ill-defined layer by fitting. Okay, so the fitting tells us that the ill-defined layer is about 85 nanometers. Is very large, and the spin diffusion length of the ALQ3 material is 45 nanometer. Okay, so this is the voltage dependence of the device. You can see here, this is 2.4 millivolts. The effect is 7 volts. And so if you go to 380 millivolts, the effect here is less than 1%. Okay, which means the larger is applied voltage, the smaller is the magnetoresistance. And this is the profile. It's asymmetric, and we have the very large magnetoresistance at a zero field. Zero applied voltage. So the reason for this is still under debate. Of course, there are some gas here. Okay, so what is the temperature dependence here? You can see at 30 Kelvin the effect is 6%, but 180 degrees the effect is almost zero. Okay, so here is the profile. The magnetoresistance goes down very fast with respect to the temperature. And as you can see, the magnetic moments of the LSMO also goes down with the temperature. So maybe the small magnetoresistance at the high temperature is relative to the injection capability of the LSMO. So this is one possibility. But the other possibility is that the spin diffusion, relaxation time of the electrons is also the temperature dependence. So which one is more accurate? So actually, in 2009, Drew et al. Reported that they can detect the spin diffusion length versus the temperature, and you can see the spin diffusion length in the ALQ3 material goes down very fast with respect to the temperature.
What is the mechanism for the spin relaxation?
So spin relaxation, I think that mainly because of the electron spin phonon coupling. So this is the definition of the spin lattice relaxation.
But isn't phonon spinless? How can a phonon avoid a spin?
This is a good question. So honestly, I didn't study very deep in this about this question. Now, thank you for the question. Because I am not the ESR guy, so the ESR they study very deep about this. Maybe you can explain this better.
So yeah, typically when you have phonon involved, when you have several spin involved, and so you have to conserve spin, and you have to couple the system.
So is a phonon shaken an impurity with a spin?
There are many different ways you can come up with. There are like so-called two-phonon Raman processes, for instance, and a lot of these relaxation processes also involve hyperfine coupling. So basically, the spin is drained into the nucleus, and to conserve energy, a phonon is involved there.
Okay.
And so,
it's
but there are many variations. But
it's phonon assisted.
it's phonon assisted,
Assisted.
but it's not just a phonon electron spin scattering. That exactly doesn't work.
Okay. Okay. Thank you, Chris. Yeah. The explanation makes a lot of sense, I think. Okay. So although the room temperature effects is very hard to get, but there's also a few groups try to get it. So the first group is reported the room temperature effects at of the P380 using P380 material as the spacer, and they get about 0.5%. The other paper, they got 1.15%, and our group also got 1.5%. Recently, Husso as our group give the effects of 5%, more than 5%, a little bit here, but the thickness here is 5 nanometer. So now go back to the questions. Is it giant magnetoresistance or tunneling magnetoresistance? So to distinguish these questions, those two phenomena, we have to detect the spin transport inside the material, and our group here did that. So I will present two experiments that I prove that actually the spin of electrons are actually transports in the materials. Okay, the first experiment that we did is about the isotope effects, in which we synthesize the first materials we call the hydrogenated D-DOO-PPV. This is just a regular polymer. And then we replace all of the hydrogens here with the deuterium atoms. So if you look into the hyperfine interaction formula, you will recognize that the hyperfine coupling depends on the hyperfine coupling constant. And the hyperfine coupling constant in the hydrogens is about 6 times larger than in the deuterium. This leads to the hyperfine interaction of the hydrogenated D-DOO-PPV is about 3 times larger than the deuterated D-DOO-PPV. Okay, and I make those devices with those materials. You can see the spacer here, and we use LSMO and cobalt. And the device is about 25 nanometer thick. The applied voltage is about 10 millivolts. Everything is identical, the same temperature. And here is the result. You can see the magnetoresistance in the deuterated D-DOO-PPV is 40%. On the other hand, the effect in the hydrogenated D-DOO-PPV is only 2%.
What temperature is that? At what temperature?
At 10 kelvins. Yeah. So if the effect is really because of the tunneling effect, you would see the same magnetoresistance magnitude here, because tunneling doesn't care if the spacer is deuterated or hydrogenated. So this is the definite proof that we have the spin transport inside the materials. And so we actually measure the spin diffusion length of those materials, and it turns out that the deuterated D-DOO-PPV has 3 times more diffusion length than the hydrogenated D-DOO-PPV.
How was this determined in the same way by looking at different sequences?
Yes. Here we make a few devices with different thicknesses and measure the spin diffusion length fit it by this formula. Yeah. Okay, so I would like to give you the second proof that we actually have the spin transport in the organic spin wells. So in this configuration, I use the bipolar organic spin wells. What does it mean, bipolar? I use one ferromagnetic electrodes for the hole injection, and the other one is for the electron injection electrode. So if you have magnetization in this direction, if you inject the hole into the material, you inject the hole in the opposite direction. This is very important issue that I would like to emphasize. So in this configuration, we inject electron with the spin up, the same with the magnetization here, but the hole with spin down. So based on the possibility the spin pair singlets and triplets configuration here, you can see that we only form the state number 3 and number 4, which means we have 50% singlet states in this configuration. And the electron quantum efficiency in this configuration is 50% because only singlet emits light. But in the other situation, you can see that the spin of electron and holes are parallel. So they form only triplet states, and in principle there are no lights in this configuration. Okay, so but the question is how to inject electron into the materials. Is how to inject the spin aligned electron into the materials. So we use cobalt. So cobalt has the Fermi energy next to the HOMO level of D-DOO-PPV. This is not good. Not good for the electron injection. But in the community, in the organic light-emitting diodes community, people study a lot this phenomena. If they put the lithium fluoride, this is the insulator materials, next to before the cobalt, they change the work function of the cobalt. So they can shift the work function, the level, energy level of the cobalt up to close to the HOMO level. So at the time, cobalt can be used to inject electrons into the organic semiconductor. Okay, so this is the device structure, and you can see that we get the quite good the device based on the IV characteristics and also EL, electroluminescence versus the voltage here. The turn on of the electroluminescence is about 3 volts, which is very important. Because if the turn on voltage here is 10 volts, it could be very bad because this, like I told you, the spin injection capability go down with the applied voltage. Okay, so this is the effect. Yes. Oh, lithium fluoride is the insulator, and this is the bipolar insulator. Yeah, the polar insulator.
And you kind of elaborated on top of this.
Yeah, this is LSMO, D-DOO-PPV, and we have the lithium fluoride and cobalt, and we have to protect the cobalt by aluminum. And the thickness of the aluminum and cobalt layers needs to be less than 10 nanometer in order to allow the light escape from the device. So, yeah.
So I'm just curious, if this is an insulator, then what is the work function in that case? Like, how do I think of a work function for an insulator? And how does it modify the work function for cobalt? Just confused a little bit.
So, because of the polar, the dipole interaction between lithium fluorides and the electrons inside the cobalt, and somehow it lift up the Fermi energy just close to the interface. This is just exaggerated. I should plot something like this. Yeah. Okay, so this is the result that we got. You can see here with the parallel configuration, we have the larger electroluminescence than the anti-parallel configuration. It's not very 50% quantum efficiency and 0% quantum efficiency here, because we in reality we don't inject 100% spin polarization into the materials. Yes.
Okay, so I understand your argument that you're making there, because you say you inject from both sides, they do recombine, otherwise you wouldn't get light out.
Yes, yes.
And if this recombination now depends on your
spin.
basically polarization.
You see the hysteresis
right.
like this.
Then your argument is that the spin state has to be conserved until they meet.
Yeah.
And that would be a proof of transfer.
Right.
Now, you have shown before that these spin valves, the current in these spin valves is also obviously controlled by your electrodes. Right?
Yes.
And you showed all basically the current diagrams. Why is the argument that your device controls your charge carrier injection, and therefore the injection, your charge carrier currents control your recombination, not applicable? Because in this sense you wouldn't need transport to explain this effect. You control current, current controls emission. This is in a way a light-emitting diode.
Yeah, this is very good comments. And actually we detect both magnetic field effects on currents and magnetic field effects on electroluminescence, and the magnetic field effects on currents is much less than this. It's about 1 order of magnitude less than this. Yeah.
And these are low temperatures.
Yeah, this is at 10 kelvins. If we go to 200 or 50 kelvins, the effect is 0.
Okay. One more question.
Yeah.
So when this is approved for spin transport,
Yes.
why do Handle experiments not work? When a Handle experiment is you have a spin that propagates, and now you apply a perpendicular magnetic field, and the spin, as it propagates, starts to precede.
Yes.
Then you basically, you would have to see a modulation of your current or photo emission.
Yes.
As a function of the applied magnetic field strength.
So far, honestly, I don't know any paper about honey effects in organic spin valves.
Have you tried that, or has that?
I don't know.
Because my understanding is people have tried and it didn't work, so they didn't report on it, basically.
Yeah, there's some reason it's very tough to do that experiment. We need the horizontal configuration to do the honey effect. But even the horizontal horizontal organic spin valves, no one has reported that structure yet. So how can they study honey effect after?
You certainly haven't tried it.
I haven't tried it yet. Okay. And I think that because the spin diffusion length is too small, so if you want to make the horizontal organic spin valves, the 2 electrodes need to be about 50 nanometer. This could be very tough. If you make it too far, 2 electrodes cannot talk to each other.
Why can't you take vertical structures?
I don't know, and I am not aware any study, even in the inorganic community, people study honey effect in the vertical. There's some reason, but I don't know yet. Yeah. So that's the reason why we are going to make the organic single crystal. So we hope that we can enhance the spin diffusion length 1 order of magnitude from 50 nanometer to 500 nanometer, so that we can easily make the horizontal organic spin valves with this. So this is the new avenue for the community too. I think a lot of groups want to grow the single crystal and study the spin transport and spin injection into this kind of materials. Okay, so now I would like to go quickly about the spin manipulation in the organic spin wells. Okay, so this is the, like I told you, this is the horizontal structure for the organic spin wells or the spin wells in general. One electrode we use to inject the spin aligned carrier and the other one to detect it. And now if you apply the magnetic field perpendicular to the spin, at the time the spin recesses around the perpendicular field here. As a result, you change the resistance of the device. And this is well studied. This effect is well done in the inorganic communities. You can see people has done very nice job, very nice results. But in the organic community, no one has been done this one yet. And we try to be the first groups who reported the honey effect in the horizontal organic spin well structure. So the second way that we can manipulate the spin of the electron is using the electric field, and the device was suggested by Data and Das in 1990. It is 22 years ago. So you can see that the device structure is similar to the horizontal device, but they use the gate, the electric gate here, in order to control the spin, like carrier transport inside the materials. But unfortunately, for 22 years, a lot of efforts have been done in this device, but in both organic and inorganic, Spintronics, but no positive results has been reported yet. So this device is very, very important for the Spintronics devices. Why? Like the transistor, field effect transistor in electronic device. This is the building blocks for the electronic circuits. If you don't have the field effect transistor, you don't have the computer, you don't have many electronics devices nowadays. So this device is very, very important. And we are at the University of Utah has some motivation that we can do this in the organic materials.
But don't you need ballistic transport for this even to work?
Pardon me?
Don't you need ballistic transport for Hanley or Data DAS
Uh,
to work? If you have backscattering, then you don't, your precision is destroyed. So you can probably conclude that you won't see any Hanley effect by just looking at the conductance. If it's not quantized, then you don't have ballistic transport.
So actually, yeah, that's an excellent point. But we are experimentalists, so and
Okay, I shut up.
and actually we can do the spin transistor with a single crystal, and maybe we can eliminate that kind of effect of scattering. Okay, so what I study is the C60 material. In C60, you can see that we don't have much hyperfine interaction and intrinsic organic semiconductor, intrinsic spin-orbit coupling. Why? Because we don't have the nuclear spin in the carbon C12, and most of the carbon here, 99% of the carbon here is carbon C12. Okay, and you can see here the magnetic response is very nice, and the effect is 10%. It is not 40% like I presented in the D-DOO-PPV or in the AOQ3 device. Why? This is the surprising results, because even if we don't have the strong hyperfine interaction and the spin-orbit coupling, but the spin diffusion length is still small, and we actually make a lot of the devices and measure the spin diffusion length. It is about 12 nanometer. This is very small compared to D-DOO-PPV or AOQ3, which is about 40 nanometer. So what is the loss mechanism here? Actually, we don't understand, we don't know, but we measure the spin diffusion length versus the applied electric field. And we actually see that there's some change in the diffusion length here. So the spin diffusion length is actually depends on the electric field. We don't understand why, but this is the experimental result. And the stronger is the applied electric field, the shorter is the spin diffusion length. And this encourages us to go for the spin transistor. So, and we hope that we can change the spin diffusion length if we apply the stronger electric field than this, because here the electric field is not very strong actually. So this is our motivation that we might achieve the spin field effect transistor if we use organic materials. Okay, so about the application, so if we can achieve the organic spin weld magnetoresistance at room temperature, but we haven't achieved it yet, okay? So we can make the read head of the hard drive by the organic spin welds. We can use the giant magnetoresistance effect to store the information here, like the magnetoresistive random access memory. This is the non-volatile memory. What does it mean? You don't need the external electric field or electric power to maintain the 0, 1 the states of the individual pixel individual bit here. So the other application is magnetic touch screen. This is actually the patents from my group at the University of Iowa. So we have the pixel, OLEDs pixel, and we can use the OLEDs pixel here as a lighter and also as a sensor. Why? Because you can see if we use the magnetic pen, bring it close to the pixel, we can change the magnetoconductance of the device, which means the pixel can detect the position of the pen. Okay. So the other application is the magnetic resonance imaging. This is also the Spintronics device. Okay, I would like to go to the summary. So I hope that I give you a brief introduction of the organic semiconductor. The transport in this material is governed by hopping transport with a low mobility. What we can do better by growing the single crystal, organic single crystal. So at the time the mobility can be enhanced by 2 orders of magnitude. So I hope that I convince you that we have some trick to inject the electrons spin alike carrier into the organic semiconductor. I introduced the first organic spin welds reported by Utah group. The effect is about 40% at low temperature. And I give you 2 proofs that actually the spin transport inside the organic materials by study the isotope effects and also the bipolar organic spin welds. And I give you 2 ways that we can manipulate the spin of electrons inside the organic materials. One is through the magnetic field, and the other one is the electric field. And we are working hard on those topics. And finally, I give you some possibility that we can use the organic spintronic device for the applications, for real application. Thank you.
Thank you very much. And the talk is open for questions.
I've waited most of my life as a physicist to wait for you guys to make organic signal crystals so that we would get rid of some of this nonsense that we have to deal with. So the question is, if you make an organic signal crystal, you still have the problem of jumping from one molecule to the next. It's not straightforward that you solve the hopping problem.
But yeah, that's exactly right. But at the time, the mobility is small because we enhance the mobility means we enhance the spin diffusion length.
But it still has to hop from molecule
Yeah, right.
It has the same problem of getting down.
The hopping gives us because now the energy level of one molecule and the other molecule are exactly similar. So at the time, the hopping is more efficient. So we don't need to overcome the energy mismatch between those molecules.
On the last slide,
Yeah.
you had an application for MRI.
Yeah.
What does magnetoresistance have to? How could magnetoresistance be?
Oh, the MRI is you detect the position of the density of blood or something like this based on magnetic resonance. So like NMR, that's we are doing. So that is actually the spin dependence, the organic spintronic device, right? Because we are doing with spin, so that's it. And that is my understanding. Yeah. Yes.
What are the prospects for growing crystal in organic?
Yeah, this is a good question, and there's the method that we are using right now is using the furnace. We have the furnace with two stages. Okay, the first stage we use to vaporize the organic materials, and the other stage is the condenser we use to collect the vapor. And if you put the quality of the single crystal depends on the temperature of two stages. Okay, you have to do and then try if the crystal is good or not. And normally you spend 2 days of growing and you get about a few micrometer thick of the crystal. Yeah, that is the way that we are doing in the lab right now. Yes.
So I've got a question, and of course I can't get over the spin transport in the spin valves.
Yeah.
With the known mobilities of these materials and therefore the known time of flight that your charge carriers have in these devices, and the known spin diffusion times that you have measured or that you've presented here, what are the spin relaxation times and what are the spin relaxation types that determine these signals? So with types, I mean, is it a T1 or a T2 process that determines this, and what are these times? Because you should be able, with a given diffusion length that you claim here and the known mobility, to extract these times, basically. On what time scales does relaxation occur?
So this is a good question, and actually I didn't put the calculation to calculate, but is it doable? I think it's about microseconds. Yeah, microseconds for the distance of about 100 nanometer, and this is just the time that people get from the organic light-emitting diodes without spin and other things.
So 10 microseconds, 100 microseconds, 1 microsecond. Can you narrow it down a little bit? Because these spin relaxation times are known of charge carriers, of polarons. I don't know. I think you use D-DOO-PPV.
Yeah, D-DOO-PPV. Yeah.
So we know what spin relaxation times in PPVs are of polarons. So the question is, does that match?
We didn't compare those. Yeah, we didn't calculate actually the. What people has reported that the spin diffusion time is about nanoseconds. Okay, in the single crystal. Actually, there's recently there's a manuscript in Nature. They try to use the single crystal for the honey effect, and they got the result, and they claim that the spin diffusion time is about 1 nanoseconds. And then the spin diffusion length in that crystal is about a few hundred nanometer. So that is only information that I know about the spin relationship time. That material is high-oriented materials like pi stacking material. I don't know exactly the material, but they have a very high mobility. Yeah.
Okay. Do we have more questions? No, then let's thank our speaker again.
Thank you.